Welcome to the 21st Annual Michael J. Buonsanto Memorial Lecture. Hard to believe it's been 21 of these lectures and still counting. Before we I introduce the speaker and begin today's lecture, I want to spend a minute or two familiarizing yourself with who Michael was and some of his contributions before we start the lecture. So I'm going to share a screen here. Everybody see that? Yell if you can see my title slide.
They can't, but yes, we can.
Okay, great. So this is a photograph of Michael in his office at Haystack, and on the right is the way that Michael often was remembered, with his trademark red sweater, which made him stand out at things like CEDAR meetings, and that's part of the reason why I have a red tie on here in honor of Michael. We've been running a lecture here annually for the last 21 years because Michael was an extraordinary scientist whose career was really cut short at too young of an age, who had a really great publication legacy even in that short amount of time. Michael had 70 refereed articles, 60 of them between 1989 and 1999, 13 as the sole author, and 25 as the first author with more than 50 collaborations. And on the right is one of the ways that Michael was most well known in the CEDAR community, was organizing a very faithful storm study workshop at which he kept us all organized at both the beginning and the end of the workshop and provided considerable momentum. And you can see more than a decade there of workshops in the formative and middle years of the CEDAR community, which studies, of course, the physics and chemistry of the upper atmosphere. Co-authors of Mike Buonsanto really span the gamut of our field at the time. Many ionospheric, thermospheric, and even some magnetosphere, ionosphere coupling people all collaborated with Michael. I will point out that 5 of them were with undergraduate student co-authors through our Haystack Research Experiences for Undergraduates program. One of the articles that he wrote, in fact, in the last couple of years of his career were this very well-known EOS article about the state of space weather understanding at the time at Earth back in 1997, written with Tim Fuller-Rowell. And then a really landmark paper just before his untimely death, this ionospheric storms review paper. And in fact, this one was so well known that today I looked up, 21 years after his passing, that has 851 citations, including you can see how many were added between November 2018 and now. Basically, that paper added about 160 citations in the last 2 years. So his work was not only prolific, it really was enduring. He was very well known for ionospheric climatology, including models that John Holt and Shenrong Zhang here at Haystack have continued, regional and local empirical models driven by, in this case, Millstone Hill incoherent scatter radar data, but then he continued, the work was continued later with John and Shenrong to cover all ISRs, including historical ones. He did a lot of education and student training. Here's 3 papers involving his RU students. The middle one, Larry Pullman was from Wisconsin. And Olivier Vitas turned out to be actually a planetary scientist at ESA, working on Mars Express, for example, and an upcoming mission to Jupiter. And Y.K. Tung, 1991, with Dwight Seipler, writing about neutral atomic oxygen density. So he had a considerable influence on students. So he was a scientist, colleague, mentor, and friend to us. And that's one of the reasons why we're keeping his memory alive through this annual lecture series. So with that introduction to Michael, I want to introduce today's speaker, the 2020 Buonsanto lecture, who is Alan Burns. Alan is a project scientist at the High Altitude Observatory at NCAR out in Boulder, Colorado. He was formerly a research fellow, in fact, at the University of Michigan at the Space Physics Research Laboratory. He is an author or co-author of over 170 papers. He's a former associate editor of the journal Atmospheric and Terrestrial Physics for 7 years, and for Journal of Geophysical Research for 4 years. And he received his PhD from the University of Canterbury in 1986. So we're really, really happy that Alan has agreed to give this lecture, which subject is geomagnetic activity effects on thermospheric composition as seen by GOLD. GOLD is a new mission which is yielding fundamental insights already. So The only thing I have left to do before introducing Alan and looking forward to his lecture is the way we're going to run the logistics here in this virtual meeting. I'm sure you will all have questions. We're going to let Alan give the lecture uninterrupted. If you have questions as you go along, please find the Q&A box within Zoom, not the chat, the Q&A box, and place your questions there. We have a couple people monitoring that. After the lecture, I will moderate the Q&A period by pulling questions out of that particular window. So I will stop sharing my screen here. And without further ado, I'd like to introduce, hold on a second. Problems with multiple screens here. Actually, Alan, you could probably just take it away from me if you wanted to. See if that works.
Yeah, it seems to.
Okay. So there we go. Without further ado, Alan Burns, I'm really looking forward to your lecture, and take it away.
Just have to try and kill a window here, I hope. Yeah. What I wanted to, I have a little bit of trouble with video conferences. I found out this morning that I tend to sometimes go a little far away from the mic, but I've been assured that I will be told immediately if I do that. Phil has read the title of this talk. What I want to do today is to concentrate on geomagnetic activity activity effects on thermospheric composition, because it was this where I first really knew Mike. And I'm going to talk a little bit about that on the next slide. But before I do that, I want to give some special thanks to people who've helped me prepare this talk, particularly Xu Guang and Quan Guan, who are both, Xu Guang's a postdoc on gold at NCAR, and Quan's at LASPAS, the other three people listed in red who are all gold postdocs and all contributed to this talk. In addition, and especially Xu Guang, Wenbin, and Liang have gone and hopefully found most of my mistakes in this talk. Now, I started to go down memory lane when I was asked to give this talk. And it's a lot of years ago. This is over 30 years ago now. So some of my memories might have changed, been altered a bit by time. But my all-embracing memory of Mike was actually at the Holiday Inn Golden Gateway in San Francisco for Fall AGU. I don't know how many of you remember the Holiday Inn Golden Gateway. It was located at Van Ness in California, which happened to be the highest point in downtown San Francisco. And another salient feature of it was there was very few restaurants around there. It was a very good fish and chip shop, but apart from that, you wouldn't get a meal. So all of the more senior scientists would stay down. The conference was held, down at the foot of Van Ness, below the Holiday Inn Golden Gateway. So the senior scientists would stay down on the flat area where there were plenty of restaurants and they didn't have to walk upwards. Junior scientists and the PhD students were put up in the Holiday Inn Golden Gateway, which involved a very lengthy walk uphill at the end of the day. But it had an advantage in that if you came from the East Coast or on Eastern time, you had plenty of time in the morning. And I have strong memories in the morning of me talking with Mike then, because we had a couple of things really strongly in common. One of them was that we were both interested in geomagnetic storms at the time. I was interested in the effects on neutral composition, and Mike was interested in the effects on the ionosphere. Not quite sure why we never ended up on a paper together, but that was such. But that meant that we had a topic to talk about, and because a lot of the people you knew weren't up in the hotel, in the morning you'd start to talk about things. And that was when I learned that obviously coming from the University of Canterbury, I'm from New Zealand, that Mike did his PhD in the University of Auckland in New Zealand. And in those days, there was no World Wide Web for people to look things up. So I didn't find many people who knew much about New Zealand. And so I can remember having some very good chats over breakfast or just sitting down and talking with Mike about New Zealand. I don't want to dwell on this too long. I was looking for a quote that I thought was apropos to this. And I started thinking of Henry V from Shakespeare, and it was just too bellicose. Mike was a gentle soul. And so I searched for a better quote. And apart from the bit I've crossed out, I found this quote that I thought was very appropriate. It says, "It does not matter if we are forgotten. What matters is the effect we have on those around us and those who came after us. What matters is how our own lives affect the larger perpetual community of the living." It's by someone called Lynn Schooler. I just thought that that summed up a lot of about why we're here today. That Mike had a really strong effect on people around him and those who've come afterwards, for example, with that review article. And so Mike has had a really profound effect on the larger perpetual community of the living. With that said, I want to do a little bit of history. I'm not going to read all of these bullets. There's two. Appleton got his Nobel Prize for proving that radio waves were reflected from high up in the atmosphere, not from the surrounding hills. And so that was really the start of this sort of study of the ionosphere. That was back in 1925. But as ionosondes, as they are now known, went forward, one of the things they noticed at mid and high latitudes was when there was a lot of strong geomagnetic activity, you got what was called negative storm effects. And I'm going to show what they are in a minute. But it became, because they were so important on shortwave communications, it became crucial to understand how they were caused and how you could predict them, because you weren't seeing them where you had aurora. You were seeing them at much lower latitudes. And Seaton in 56 first suggested that neutral composition changes may be the cause. And that, to a great extent, is the motivation of today's talk. And I will, at the moment, not mention any of the other things in here. So what is a geomagnetic storm at Millstone Hill? This was deliberately, this figure's a little bit deliberately crude. It was just straight downloaded from a website. And it shows something called FOF2, which is the maximum frequency that is reflected back to the ionosonde from the ionosphere, hence the F2 peak bit. And it is proportional, if I've got the order right, to the maximum electron density in that peak squared. It's either that or that. So what you get is a trace of the maximum peak electron density. And you see what you see is this period here in 2012, in March, when a large geomagnetic storm occurred, and you can sort of look at the end during the daytime, and you see roughly what the expected electron density at that time was. As the storm came on, you got what is a very common feature, and this is at Millstone Hill. This is on the 6th of March 2012. You got an enhancement of electron density at Millstone Hill. So we're in mid-latitudes. There's a chance that the aurora was overhead, but it was probably equatorward of the aurora. It depends on the time of day and a few other things. But the next day, the electron density in this particular case in the daytime was about half that of the approximate quiet time reference. And basically the ionosonde couldn't make measurements at night because there was too little signal coming back from the ionosphere. So it was probably a very weak ionosphere. Typically you get much greater decreases at night. So you get this negative storm in the ionosphere, and this was the stuff that they were finding in the 1930s. And this was sort of a fairly common behavior at mid-latitudes. This is more of a global perspective. This was something that Jing Liu, who was a postdoc at NCAR at the time, now has a faculty position in China. He looked at the Madrigal database there at Millstone Hill and compared it with a quiet reference. And a lot of this talk is about what quiet references really are and what we've learned from gold. But this will do as a quiet reference because it shows the main features. By using the global TEC data, you can see the negative and positive storm effects very clearly. Basically at high and middle latitudes, you're getting these great decreases of TEC. And this goes on, I only want to look at the left-hand side here. This was during the St. Patrick's Day storm, and it's running from -80 to 80 latitudes, and this is 24 hours of local time at UT16. But what you see are these really strong negative storm effects, and this is the stuff that Seaton was attributing to neutral composition. And I now want to go on to describing why the neutral composition is likely to change at mid-latitudes during storms. And to start with, I'm going to give an equation which I use like doing in talks, but this is a nice simple equation. This is it appears to be a nice simple equation. When you really get into the details, it isn't. But if you assume the O plus continuity equation and the ionosphere is mainly O plus at 300 kilometers, you get an equation for the time rate of change of O plus, which is the ionization, which can be through solar ionization or precipitating electrons in particular, ionized neutral atomic oxygen. The neutral atomic oxygen undergoes chemical recombination primarily with N2 and O2, and we've got a weekly temperature-dependent reaction rate for that reaction. And so this is essentially the way the O plus is lost. And then you have transport, and that involves moving it somewhere else. In the 1980s anyway, Henry Wishbeth demonstrated, as long as you used pressure surfaces, that during the daytime, most of the O plus you got at mid-latitudes was straight from production and loss. So if we assume there's no transport, and we assume that there's no time rate of O plus, we can derive a calculation of what the O plus density should be. And essentially it's this ionization rate times the density of O divided by this recombination rate, which I said is slightly temperature dependent, but not much, times the concentration of the molecular species N2 and O2. So if this ratio changes, the O plus density will change. And this is the principle behind having negative storm effects. By 1981, Gerd Prols had done a lot of work with mass spectrometers flying in low Earth orbit satellites. And he was able to build up basically a climatology of a weather effect. That is, what is the average behavior during storms in this negative storm region? And between him and a few other people like Hans Meyer, they had the basic principles of what happened. And I'll go through those principles a little more in the subsequent slides. Basically, though, you get upwelling around in the region of Joule heating, and you get the winds blowing across the polar cap, then drive that into the night side, and it co-rotates into the day side. We're actually going to find some very big twists on this in the quiet time results from gold. Well, as a single shot confirmation of this, Doug Strickland used polar, I believe it was, and an FUV, the FUV imager on polar, and showed that this dayside pattern is exactly what you saw in the data from this FUV imager. In other words, you were getting these depletions in very much the same shape. So this isn't just a climatology that doesn't apply locally. This is something that's going to occur as a weather effect during storms. Polar was in a very unusual orbit a long way out, so it was actually very hard to get a sequence of images to see things developing. And that is important to when I get to gold. Well, the first thing I want to talk about is geomagnetic storms and neutral composition, and why on Earth neutral composition can change during geomagnetic storms. And perhaps the most important thing to remember about this is that the upper atmosphere is heterogeneous, not homogeneous. So if you shift things vertically, you change neutral composition. And this was just an eye candy picture, which I thought was very beautiful, by a man called John H. Moore. This was taken at Crater Lake in Oregon, and you can see the entire sweep of the Milky Way and then an aurora. For those in the know, Crater Lake is at a pretty low geomagnetic activity, so this had to have been a large geomagnetic storm. Well, here's another image of precipitation during a geomagnetic storm. This is one of the things that happens in a geomagnetic storm. There's particle precipitation around the auroral oval, as well as producing beautiful aurora and ionizing more of the gas, so your ion densities and electron densities are higher. Actually, I think that was the other thing. But it also expands to quite lower latitudes. So this one, for instance, would have been seen over Millstone Hill. Well, it isn't the only thing that happens at high latitudes during geomagnetic storm. The ions, because you have the solar wind flowing across the high latitude area of Earth's magnetic field, you set up a convection pattern where you've got E cross B drifts going in this classic twin-celled pattern. And basically, on the outside of the convection pattern, the drifts blow towards the day side. And in the center of the pattern, they drive towards the night side. And Tim Killeen, this was a cover of GRL in '85, demonstrated that the neutral winds tend to be constrained to follow this convection pattern using Dynamics Explorer 2 data. Another thing that happens is when you've driven the ions very fast, the neutrals are not flowing so fast and they may be actually moving in a different direction. There's still 1,000 neutrals for each ion, but because the energy is so high in the ions, it has a profound effect on the neutral atmosphere, not just the kinetic energy transfer I was talking about earlier. That's probably only about 10% of the energy loss, and precipitation is another 20%. About 80% of the energy loss from in the potential pattern or in the high latitudes is because ions collide with neutrals. They impart heat to the neutrals. Ions heated, but it's still driven by the convection pattern. Hits another neutral, it hits another neutral. The ions get very hot. The electrons don't, which is kind of interesting. But eventually those ions, or not eventually, pretty rapidly those ions thermalize with the neutrals. So you transfer ultimately all of that heat that has gone into the ions through frictional heating and transfer it to the neutrals, so you get much hotter neutrals. And this is just an example of a figure that Shiguan Kai produced for me. This was actually a quiet time but it illustrates where you tend to get the Joule heating. And I'm not going to show it, but later I'm going to mention that you also, in certain conditions, get a lot of Joule heating over the polar cap. But mostly in normal conditions, you get a lot of Joule heating around the auroral oval because that's where the ions are, mostly. Well, one of the things that happens when you get a lot of heating is you get a lot of temperature rise. And this was a storm observed by DE2 in 1982, by DE2 in late 1982. And this was notable because it was the only storm we could get from that period that actually showed a decent sweep of temperatures. This is northern latitude from 0 to 0. The right-hand side is 1800 local solar time. The left-hand side is 600 local solar time. DE2 was in a polar orbit. And these are temperatures in Kelvin. They're running from 1000 or 1200, which was about the quiet time temperature, up to 2200, which was the storm time temperature. And these are neutral wind changes, so not neutral temperature changes. So they really represent a lot of heating. And in fact, during one storm, I saw a temperature that actually reached 2500 Kelvin. But the other thing to notice is these temperature changes are not constricted to high latitudes where the precipitation is. They're occurring at much lower latitudes. And right at the end of this talk, I'm going to briefly discuss a period in late September of this year that we've been looking at sort of as a mini campaign with the postdocs in gold. And I'm going to show an example of the change in global temperatures then. But this talk isn't primarily about temperatures. And the last thing that I want to show you is something I alluded to when I was talking about kinetic energy transfer. The black in here, which is a bit hard to see, this is again Zhu-Guang-Kai's plot, is the ion convection pattern. And the white is the neutral convection pattern. And one thing you notice, particularly on the evening side, is that the neutral winds are constrained to follow the ion convection pattern, particularly, as I said, on the evening side. But when you get into the night side here, a strange thing happens. The ions are still constrained by the magnetic field. So they're forced to bend around and head back to the day side because of the E cross B drift. But the electron densities are small on the night side typically. And there's nothing to stop the neutrals. So you get this jet of neutral winds flowing to very low latitudes. And this is a schematic I developed a number of years ago about this. This green circle is approximately the auroral oval. And the green arrows are the neutral winds that would be if you didn't have geomagnetic activity. So they basically blow from about 4 o'clock in the day side to 4 o'clock in the morning. And but when you have a storm, everything changes. This strong jet blows into the midnight region, and that causes heating of neutral gas at mid-latitudes. And that really suppresses the diurnal tide. And this suppression of the diurnal tide is one of the most important reasons that you get heating at low latitudes. You've dumped a lot of heat out into the, so you've dumped a lot of disturbed composition, high N2 and O densities out into midnight, and you then suppress the tides. This causes heating, but it also causes downwelling. And so you increase the atomic oxygen species outside this. Closer into the auroral oval during the day, you tend to get outwelling. This is a schematic, and reality is more complicated than that. But this is why you get the pattern that Prost developed that I showed you earlier. I'm not going to dwell on this. You basically get a tail. So the last part of this introduction that I want to show is goofy. This was a storm in 2003. I think it was the Jeff Crowley developed this diagram for. And it shows the negative storm effects. And because goofy works effectively on a pressure surface, it also shows enhancements of O2N2 in a positive sense. It goes up, O2N2 ratios increase during storms because you have downwelling in these regions. It looks like you've got very thorough coverage, but if you look closely, this is a day's data. This is a day's data. And so if you're looking at any point on the Earth, you can only see it once during a day. And that isn't very good if you want to try and understand the development of a geomagnetic storm as a weather system. And that's where gold comes in. This is basically our introductory material on gold that we've used for some years, and I hope most of you have seen it. Gold was a mission of opportunity, and it was designed to study how the upper atmosphere responded to solar and lower atmosphere forcing. And I'm going to go to this for the last point. I was reading about weather forecasting a year or two back, and one of the things that kept being emphasized was that the view from geostationary orbit was revolutionary for weather forecasting, because for the first time they could, this was Hurricane Sandy in 2012, this funny whirl, but they could associate things that were happening over here with things that were happening here. They could follow the progress of thunderstorms. And what we're already finding with gold is we seem to be getting a pretty much an unprecedented view of how the upper atmosphere changes, and we can easily relate between longitude, local time, and universal time effects. And that is a really powerful tool. We've still got a long way to go through truly exploiting this. Well, gold was framed by the very questions we're discussing here. And there was one about geomagnetic storms. There was one about solar EUV radiation affecting the upper atmosphere. There were how things below affected things, and how the nighttime equatorial ionosphere influenced the formation and evolution of equatorial plasma density irregularities. And we were a little bit worried about this one because we weren't sure whether we had enough signal to see them, especially when Goofy, after the experience of Goofy, where they didn't see them after about 2007. They may have seen them since then, but in that solar minimum, they weren't seen. I don't have a great picture for showing you that we see them a lot in gold, but I do have one picture and I'll show that later. Well, I want to go through this in a slightly different order. First of all, I want to show a couple of slides about how the lower atmosphere, we could determine the lower atmosphere was affecting things, data observed by gold. I'm going to skip that, a bit short of time. So this is the lower atmosphere effects. This is a paper by Jens Oberheide. It was published quite early in the gold mission. We were really lucky because there was a very large but not major southern stratospheric warming in the southern hemisphere during the first year of observations of gold. And what Jens did was he's got the latitude here from 60 to -60 and the day of the year here. And he was showing how the O2N2 ratio changed and associated it with a measurement of the southern stratospheric warming in the stratosphere. And as you can see, there was this tremendous correlation at low and low middle latitudes between gold's O2N2 and this changes due to the stratospheric warming at the same time. And this is actually a difference which shows it up even more clearly. So it's clear that we've got a really strong influence from below here. We've had a sudden stratospheric warming, and it has strongly affected neutral composition. Quengran did another thing, well, although I've attributed it to his paper in 2020, I don't know if this made the final cut. He was looking for the 16-day wave. We don't think it's directly the 16-day wave. We think it's probably the modulation of tides. But when he looked for it in radiation, he found a really strong signal at the right period. One's north and south, and I don't have that information handy, but we can see that the wave comes through quite clearly in these data. Now we come to the crunch. We're completely at solar minimum. And so if we look at EUV effects, this is slightly exaggerated, but virtually nothing happens. So there's not a lot we can do. If you look at geomagnetic activity, you get something fairly similar to this in terms of if you plotted KP from 0 to 9, you get it all in the lower part. But luckily with geomagnetic activity, we could look at what was happening in the quiet time. But the EUV was changing so little that it shouldn't have been causing much in the way of changes in the gold data, and we see no evidence that it has. Well, this is work that Xuguang Kai has been doing. Basically, we've done a series of studies, and alluding back to things that I said earlier about storm quiet comparisons. You need a quiet comparison. I don't know about anyone else, but I've always thought, oh, it doesn't matter too much as long as you have a KP below about 5, because storms happen nominally with KP greater than 5. So what Xuguang did first in these series of studies is take a look at geomagnetic forcing in active conditions. And these are 3 examples in 2019. This is day of the year. I think I've distorted this somewhat. So this goes 146 to 149. So that should be May. 153 to 160, 157 should be getting into June, and another June 162 to 166. This blue line here is KP, which you can see on this side. It runs from 1 to 5. So you're getting KP in here in the moderate range in the second half of this period, and it's pretty quiet beforehand, which at this stage we thought was a really great way to make the comparisons. We'll actually show down in the next series of panels that it is. But each of these periods is like that. So if we look, this is the AE index, which is a much better indication of geomagnetic activity than either of the top 2. And you can see that in fact during this period, maybe not so much this one, but it was pretty quiet between 145 and 147. So if we difference 145 and 146, there's very little change in neutral composition. It's probably within error bars. Similarly, 153 to 154, 162 to 163. These are gold data and that slightly different UTs, 13 UT at this time, 12 UT at this time, and 10 UT at this time. But when we went to the bottom and we went to moderate conditions, I think is the safest way to say it, particularly here in the middle and the right-hand side, we got these changes of O2N2. These weren't minor changes. These were minus 20%, minus 30%. So even in these moderate conditions, we're getting changes. How we know that they were large changes, how we know they were associated with geomagnetic activity was that we're able to simulate these events with the TI-EGCM using WIMA. And you can see, well, they're not one-on-one identical. The bottom is the TI-EGCM, the top is the gold data, and the TI-EGCM is run for the appropriate conditions for these days. And you can see it's producing this mid-latitude depletion, and at a similar magnitude, -20, -30. And it's, in both cases, we're running up from about 0 northern latitude to about 70. So we're producing the same thing at the same place. We have more information about why they occur, but I don't want to talk about that today. So the TIAGCM doesn't allow any change. It doesn't allow any rapid changes in the forcing from below as it's configured in its standard configuration. So these changes, which are very quick, can't be being forced from below. You saw the EUV, they can't be there. It can't be the result of that. So it pretty much eliminates, and we did some composition forcing analysis to demonstrate this, pretty much originates because of this geomagnetic activity. And it's another story as to why geomagnetic activity can cause these large changes and ostensibly only moderate geomagnetic activity. The other thing is that this feature dwells for a long time. So instead of acting just as a force system, it's acting like a weather system. I don't think we highlighted that, but we started to wonder what a quiet time was and whether we could make comparisons. So we started looking at Q conditions, and we'll get to AE in a minute. But this is KP now. It's running from 0 to 2, this is the blue line. It's never any higher than that. However, when we looked at the auroral electrojet index, we saw that there was quite a bit of activity there. And gold is seeing again quite large changes in O2N2, 20% here in the mid-latitudes. This is a slightly higher latitudes, 40 to 60. But it wasn't what we expected when we started doing this. And the latitude again is pretty much as it was. And these are longitudes, the gold's in the gold field of view from -20 to 30. We also plotted this against TEC from the Madrigal database there in Millstone Hill. And lo and behold, we were finding these holes in mid-latitudes occurred in exactly the same place and at roughly the same magnitude. So it's almost certain that these are being driven by those composition changes. These lower latitude changes are certainly not driven by composition changes, but I don't want to discuss the electric fields today. You'll notice these were TIAGCM simulations. We saw some of it, but not everything. And I'm going to skip this just before I go to the storm. I just wanted to say that we were trying to work out why these low KP resulted in strong AE and strong neutral responses. And this would be close to Dolores's heart. In these conditions, it seemed to be that BY was generally quite a lot larger than BZ. And one of the strange things that we were seeing in the model runs was we're getting a lot of dual heating over the polar cap. In those conditions, the neutrals are traveling at in a very different direction from the ions, which leads to across the polar cap, which leads to really strong changes in geomagnetic activity. Now, I'm beginning to run short of time. I have about 4 minutes left. I just want to talk briefly about the storm that happened, I guess it's a month ago now. And what we decided to do when we saw that we finally had a storm was sort of do a mini campaign with the gold postdocs. Richard and I weren't particularly expectant of getting anything new from this, just thought that it's a good way to work the data and to discuss how things work in the thermosphere and ionosphere. But we've now found all sorts of things, and I'm mainly going to show you some of the other stuff. We've got some of the earlier stuff, we've got some later stuff that's quite spectacular. But this storm was a CIR storm, and it's a fairly complicated picture. I am not going to spend too long talking about it. The two things to note here are the IMF, and watch where the red line is, if I remember it correctly, yeah, the BY is the blue line, BZ is the red line. So watch when BZ is on the negative side of this line. And that's when you expect a lot of geomagnetic activity, but you can get some. So the strong days in here were the 24th, and the one we've been concentrating is on the 28th. The activity on the 26th here was mainly a case where BZ was northward and larger than BY, so we didn't get a very strong response that day. The other odd thing to notice about this is the rise in solar wind speed. This is a CIR event, Corotating Interaction region, where the fast, high-speed wind from one sector of the corona catches up with the slow-speed stream. And it was a very gradual rise, which wasn't what I was expecting when we first saw these data. And these plots are rough because that's what the sort of thing we've been looking at. It's just a first look. Now, this is something that Fazlur Lasker and Richard Easties produced. And this was the global temperature. If you remember back to the plot I showed of the DE2 temperature during a storm, you were getting a lot of heating away from the auroral oval. Well, this is now the global average of it. If you looked at the high latitudes, you'll get quite a larger increase in temperature. Because we're averaging so much, the gold data is pretty non-noisy. And so we can quite safely say that the 60-degree increase of temperature is quite real. But we see it ramping up on the 24th, reaching a maximum about the 30th, and then cooling off again. In other words, we've got this large temperature increase as a result of the storm. And this will be coming to papers near you fairly soon. The other thing I want to show from this is one of the strange behaviors we notice about the equatorial anomalies. And this isn't the best picture to show the bubbles, but if you look on the left-hand side, you can see a bite out, and that's a bubble. But on the 28th, when the storm was occurring, we had quite a normal equatorial anomalies. The southern one was stronger than the northern one, but they ran pretty much in parallel either side of the magnetic equator. On the right-hand side, we saw something, and this is Crown Gan's picture, that we see quite often, which is that the two anomalies in this region over the Atlantic particularly, the northern anomaly seems to merge with the southern anomaly. And at present, we have no idea why this is occurring. I'm going to show that. I have to get off now. These are the plans for the new science from Gold. And as this will be online, you can take a look at these there. Don't think I need to say the conclusions. And so I'm down to answering questions. Thank you.
Thank you, Alan, very, very much. I don't know how to, I'm going to do that on behalf of everybody here online. That's the one thing that seems to be missing from these virtual things is the ability to reward the speaker. That was really excellent, and I appreciated the background as well as the new results you're giving. It's generated a number of questions, so I'm going to go through these, and just as a reminder to the audience, if you have questions, please type them into the Q&A box, not the chat. It's a little different box on your Zoom client, and then I can address them as we go. So from Larissa, she mentions, if you go back to slide 31, if you can move backwards there.
The slide is on it.
There you go. She says there are also significant positive changes in both gold data and the simulations to the west from negative O to N2 ratio changes. Can you make more comments on them? How often did they get seen? How extended in time are they? And how extended in longitude or latitude?
In these sort of conditions, they are very common. You have to be a little bit careful about the stuff right on the edge, as we've got in the middle plot. But if you look at the right-hand plot, these are quite clearly there on the west and particularly to the south and east. And when we get these decreases, we generally get in O to N2 at one location, we generally get increases next to them. And we can explain them fairly easily. Well, I think you'd have to look at the paper because it's a bit hard to see on the screen here. But if you look at what the neutral winds are doing, we're getting convergence in these regions where we're getting positive effects, and we're getting divergence in the region where there are negative effects, which means we get upwelling and heavier molecular species brought upwards in these regions of negative effects, and downwelling and lighter atomic species being brought down in the region of positive effects.
Thanks. Dolores Knipp, our last year Buonsanto speaker, says, can you explain a bit more, if you go to slide 16, and she's asking if to maybe explain a little bit more about the tidal interactions and suppressions in the cartoon there related to composition changes. I think that actually is, I was going to ask the same thing. That's an interesting model.
Yeah, this is a cartoon. Really, it was Gerd Prohls's picture here. This was built up from a very large number of storms. I don't know how many of the audience knew or knows Gerd Prohls, but he was very painstaking. Something I could also say about Al-Hadin. So Gerd went to a lot of trouble to collect all of the data from all of the storms that he could from various satellites prior to creating this image in 1981. One would assume in doing that, that influences from below are largely averaged out. So this represents the bit that's geomagnetic activity. And if you look at Doug Strickland's picture, which is a pure single image, you see that most of what you see is a very similar pattern to Gerd Prohls's. So it's probable that whatever's going from below, when you get these large geomagnetic storms, it's probably dwarfed by the changes you get in the geomagnetic activity, at least at high latitudes.
Right. Thanks. Okay, so, and I'm taking these questions in the order they're coming in. Shenrong Zhang at Haystack asks, what's the sudden stratospheric process that leads to O to N2 depletion, either mesospheric or thermospheric? Are we talking about mesospheric or thermospheric warming and then thermospheric upwelling in the southern polar region? Do we expect a corresponding TEC reduction when that's happening?
That falls into the category of questions I wish you hadn't asked. You know, we were able to simulate this. I know Larissa has shown in past years that you can see changes in the low latitudes during sudden stratospheric warmings and changes in the ionosphere. We thought in the days we were discussing those things, it was probably the E-region dynamo that was causing the changes in the ionosphere. And this is really the last part of Shenrong's question, which is the only one I can answer for sure, is that we're getting these changes of O to N2. There's no reason not to believe that these changes in O to N2 are also occurring at F-region heights. Whether this is the major process for changing the ionosphere there, or whether it's the electric field, we don't know. The way we think that O to N2 at 160 to 200 is changing is that the SSW is modulating the tides. And so we're getting different tidal forcing. And in a seminar I gave at NCAR 2 years ago now, I was showing that vertical advection associated with the semidiurnal tide is very important for heating and cooling the thermosphere. And it's also going to be very important for changing O to N2, which I didn't show there. So I think, and this is an I think, not an I know, I think that what's happening here is we have an SSW that's going through the mesosphere. It's altering the tides. They come up and they alter the ability to lose heat from the upper atmosphere, and they have vertical and horizontal winds associated with them. So you get differential changes in composition, but there's an awful lot of wild guesses in there.
Sure. And Larissa, I will request that you type some things into the chat if you can, maybe, because she's volunteering some information. I'd like to get some other questions, but for those of you, open your chat window and hopefully she'll put a bunch of things in there. So our friend Endawaka Yitzengao asks on slide number 32, so forward a little bit.
I put these numbers in.
Yeah. This is about the TEC depletion and mid-latitude. It seems localized, surrounded by enhanced density at the north and the south. Do we consider this as a composition change due to Joule heating?
Well, I mean, what you can say from these figures is that there is a composition change in the same place. We know that composition is going to change the F2 peak density, and we know it's in the right proportion. So I think the blue region is probably associated with this O2N2 depletion. Whether there's other things affecting it, I don't know. Because TEC, as you know, is basically the changes at the F2 peak plus the changes in the topside scale height.
Sure.
So there's some complications, so you shouldn't expect a one-to-one correspondence.
Agreed.
In terms of the positive effects seen in TEC, one of them here at 30 degrees may be associated with changes in composition. I don't think any of the others can readily be explained that way. Certainly the low latitude stuff is almost certainly a change in the electric field, which is kind of interesting because why is the electric field at low latitudes changing so much?
Right.
I don't have an answer, I just have a question.
Sure.
The stuff over from 0 to 30 degrees longitude, there doesn't seem to be any correlation with composition. Mm-hmm. One of the arguments might be that it's a change in topside scale height for some reason.
Right. Okay, an instrument question. So Gia, you asks, what's the typical gold temperature uncertainty? I know that you had a scalar plot where you were showing the mean temperature going up, and I guess the wonder is, what's the uncertainty on that measurement?
I can't give you the uncertainty on this picture because our uncertainties, I think Faz Lowell and Richard probably could, but I can't because our uncertainties are really based on how big our bins are. And our standard bin is 250 kilometers by 250 kilometers, and mm-hmm. our uncertainty is about 60 Kelvin. When we bin it up over, 6,000 kilometers by 6,000 kilometers, our uncertainties get really small, yeah, which allows us to do this sort of study.
Okay. Michael Mandillo says, negative ionospheric storms rarely occur at equatorial and low latitudes. So does the O to N2 depletion associated with upwelling effects at mid-latitudes explain the O to N2 enhancement at the equatorial sites?
Let's see.
We're not giving you easy questions here.
Which slide?
I think he's just saying that when you see upwelling O to N2 depletion at middle latitude, he's trying to relate that to the O to N2 enhancement at equatorial sites. I think he's wondering if there's a coupling there, maybe due to upwelling.
I'm not sure if we're talking about the little bits right here on the edge. I don't have a tremendous amount of confidence in them, but you can see even in here that there are enhancements of O2N2 equatorward of this region of depletion.
Right.
And if you go over to the model results, you can see that you get very similar enhancements. And one of the things that we've been finding, either from Q conditions or somewhat active, I think active's the wrong word, I should have used moderate conditions, you get very similar enhancements there. And when you're getting these active conditions and quiet conditions, the thing that really surprised us is you seem to be changing the neutral wind pattern everywhere. And we've been doing some work on trying to understand how it changes associated with this region of depletions. We haven't got to the low latitudes yet, but it will primarily be the result of downwelling associated with the greater convergence in this region in this active condition compared with the quiet time reference. So this is always a differential plot rather than an absolute plot.
Sure. But I think his point, though, is important that, you know, identifying where transport due to upwelling might be altering the picture that might, in fact, be important.
Yeah, but also identifying where downwelling is occurring is equally important, because that's what's giving you the positive effects.
Gotcha.
So this is the result of, we know from the model that this is the result of circulation change with the horizontal winds that alters the vertical winds. There's also some horizontal advection, quite a lot of horizontal advection going on with this depleted region, because it tends to form and stay there, and then it's blown around by the horizontal winds.
Sure.
But this region at low latitudes is probably primarily a change due to the vertical winds.
Okay. Franklin asks, is it possible to use gold data to help understand when and where electrodynamic effects are important related to neutral effects, and can you in fact untangle them and tell which one drives the other?
Interesting question. I would say that it is, I'm not going to say anything quite precisely yet. One thing that you can say from this plot is that composition can't possibly explain this region of enhancements at lower latitudes than 20 degrees.
Right.
So if you remember the O plus continuity equation, you're probably down to two possibilities, which is the three possibilities: electric field, the neutral winds, and ambipolar diffusion, because they're the three transport terms. So this is almost certainly a transport effect, but transport effect, of course, is connected with the composition effect, because transport is moving things in and out of where you can have a lot of recombination. So to a certain extent, you can untangle them. It helps a lot if you have a model run that reproduces. I'll show this one because it does. I think we have TEC on this day, but it's not shown. If you have TEC on this day, I'd almost guarantee that there's quite a strong positive effect down here. And if your model's reproducing it, then you have a really good chance at untangling the whole mess. If your model isn't reproducing it, and that's been one of the problems with the TIEGCN looking at night side gold data, TIEGCN is just not getting it right. We're still working on why, and WACMX seems to get it a bit more right, but not a lot more right. So if your model doesn't agree, you're basically restricted to what you can know from the data, and you can make sort of broad generalizations like that this TEC enhancement is not directly associated with neutral composition. But getting into the nitty-gritty is a lot harder.
Sure, sure. Okay, so Chao Zhang from GFC Potsdam says, how often does the merging happen between northern and southern EIA crests, similar to that example that you showed, which I thought was really fascinating?
I don't have any handy. During this period of the storm study, we were somewhat amazed.
Yeah, you've got that one. There you go.
From about the 20th to about the 1st, we saw this merging 3 times, but that seemed to be an exceptional case. We didn't seem, this is hot off the press yesterday when we were looking at that, it didn't seem to be directly related to geomagnetic activity. And so we've got a big question mark at the moment about the cause of it.
But this isn't a single event, I guess. I guess maybe that's behind the question.
One of the things that we're trying to do is get some statistics on this, because we've seen this happen quite a lot, and it generally happens in the same place, which unfortunately for the ground-based communities over the Atlantic Ocean.
Yeah, we'll work on some
Probably
ships.
yeah, probably why it hasn't been, if it has been reported, it hasn't been widely reported before.
Sure.
Simply because if you have a satellite in low Earth orbit, you'll just think that it's probably a mistake when you see it. And if you have a ground-based measurement, it's generally not happening overhead, so why would you notice it?
Well, I think that, Alan, gets back to the gold geosynchronous view, frankly, uncovering some things that you just don't necessarily see because of slit camera problems otherwise.
That was one of the exciting things that that we were seeing during this storm that I wasn't telling you.
Sure. So Wenbin Wang says, asking which altitude or pressure surface, isocontour, does N2 upwelling occur due to Joule heating?
You've got to look at where the Joule heating is, and you have to remember what part of Joule heating is important, and also the process by which upwelling occurs. I, for years, thought that the upwelling was occurring, that upwelling was the driving force. You put Joule heating in with upwelling. The problem is that the important source of Joule heating is really the Joule heating per unit mass. And that maximizes about 300 kilometers. And as you can see from the composition changes at 160, the composition changes are occurring at a much lower altitude. And Wenbin and I have actually been talking a lot about this. The upwelling isn't occurring because you drop heat in the bottom, like you drop a pebble in the ocean, the wave propagates upwards. If you look at it, it's occurring above 200 kilometers. It occurs simultaneously at all heights. And that is not consistent with an upwelling driven event. It has to be really surprisingly pressure wave driven event. You put the Joule heating in a column, that forces a horizontal wind equatorward. And once you've done that, you get a divergence in the region of Joule heating. And that's what causes the upwelling. It's sort of an odd thing. Wenbin has done a lot of work on this too.
Sure.
And you only really get to that answer when you look at the large waves that are generated by changes in geomagnetic activity. And if you look at them, they don't have any phase shift about 200 kilometers, but they're actually retarded below that height, but they're moving at the same speed as the waves above 200 kilometers, which means that they're being generated later at a lower height, and they're being generated simultaneously above 200 kilometers. You can see them right down to the mesopause, and Wenbin has a paper on that, which is well worth reading.
That's an interesting mechanism. I hadn't even thought about that before.
Well, we didn't until we were trying to explain these waves and how they were behaving.
Sure. Mani Sivakandan has asked a couple of things, and I'm going to actually select the last one because I'm a little bit aware of time. We've got a couple more questions here. So Mani asks, if temperature enhancement is more in high latitudes during storms, can you expect the same kind of neutral composition changes you're showing in the southern hemisphere also? And of course, if it's different, why?
It's different in the southern hemisphere because you're in a different season in the southern hemisphere typically. And it's been known from back when Gerd Pols was doing this and long before that, that the enhanced N2 densities or O2 density regions expand much further in the summer hemisphere than the winter hemisphere. They're very restricted in the winter hemisphere. And the reason is that the normal circulation moves in the same direction as the geomagnetically forced circulation in summer and moves opposite to it in winter. So you tend to get a convergent region in winter at 40 or 50 degrees in the winter hemisphere. In the summer hemisphere, the depleted region can expand, and I've seen in GUVI data, expanding all the way across the equator on a number of occasions.
Excellent. Anthea asked a question. But Richard Easties, who of course is on the gold team and is the PI, already has answered it. So Anthea, you'll forgive me, but I'm going to move to Han Lee's question as the last one that I see here. So Han Lee says, one possible way to examine if transport or circulation is playing a role in the O to N2 change is to look at temperature change. So he's asking, does temperature show a cooling where O to N2 decreases at high latitude and then warming, say at equatorial latitudes where O to N2 increases? So the question is, can you explain some of this with a temperature sort of thought?
I'm just trying to look for the D picture is probably the best illustration of this one. If you look at this picture, the temperature increase is much greater at high latitudes. But what you get are these large temperature increases, and you get these also big dips in temperature. You're putting a massive amount of joule heating in at high latitudes. You're also causing a large change in circulation that can result in, particularly at high latitudes, compressional heating. But there are places in the high latitudes where, relatively speaking, you've got divergence and you've got a lot of cooling. At low latitudes, you tend to get a much smaller temperature increase, and you don't get the temperature decreases so much.
Yeah, and he typed while you were answering that, he also means during SSWs. Oh boy.
I'm not cursing, I'm just trying to think of how to answer this. There's SSW.
Obviously a hot topic.
Yeah, what I get from Jens's picture, which is probably nearer the limits of my expertise on this, Hanley or Larissa can answer this probably much better than I can. But what you see is that the SSW effects seem to mainly be clustered around the equator. You're getting much smaller changes at higher latitudes.
Right. Yeah, that's true. So Hanli and Larissa, you should start another email thread with Alan and follow up on that. I think that would be great. Okay, Anthea, to close this out, Anthea was asking about a particular streak that was in one of the imager data. I think it was
yeah.
And Richard pointed out that there's some radiation, effects that do affect the imager. And Richard and Anthea is saying, are we talking about near the SAA? Is that area in your images due to, is there more background radiation, more noise? Do you have to be careful with that particular area?
What? No, the answer to that is no. We don't seem to see the South Atlantic anomaly at all. What happened during this week, unfortunately, this was part of the reason for emphasizing this was basically first look data. There were very high background levels on this during this particular week. And I think we had one day where we couldn't see anything at all because of the background levels. But this streak is a result of the high background levels. And with further processing and going back, we should be able to remove this sort of thing. This is one of the reasons why it's always better to use the data that was measured a long time ago if you're really if you've got real problems like this with the background level.
Always the case for emission is that as the data gets more refinement, yes, the earlier data sometimes ends up becoming resolved or new areas, and that's a good thing, I guess, for people to remember about gold is that you are constantly working on that. Yeah,
that may be the most important thing that I've said today. We were unlucky in that we get our first storm that we can really study well. And it coincides with a week where we have really high background levels. Don't seem to be the result of the storm.
Sure. Well, it is the ascending phase of solar cycle 25, so we can cross our fingers. Yeah. Okay, and with that, I think we've reached the end of our questions. I'd really like to thank you, Alan, once again for a really excellent lecture and for fielding a number of quite interesting questions. Normally, Alan, if you were in person with us at Haystack, we would have a little presentation of a plaque that kind of thanks you for doing the lecture. We'll be in touch about that. But in the meantime, as Anthea said, you know, I'm going to clap on behalf of everybody who was here. We really appreciate all of you joining us for the Buonsanto lecture. Please, we hope you can join us again next year. And so from Haystack Observatory and the Atmospheric Sciences Group, we will tell you good evening, good morning, or good afternoon. And thanks again.